This will be the last lesson in basic calculus. At the end of this lesson, you are expected to compute and evaluate the area of the plane region using the definite integral, and to solve problems involving areas in the xy plane. For our first given, find the area bounded by the curve y equals 5x minus x squared from x equals 0 to x equals 6. Using the calculator, the result is this. By following the assumptions of definite integral in interpreting this problem, the graph is situated on the right. That area is bounded by the graph itself, the x equals 0, x equals 6, and the x-axis. And on the left, I show the solution why we have that 18. The small f is 5x minus x squared. The antiderivative of this function is 5x squared over 2 minus x cubed over 3. I am showing now the other way on how to evaluate this function. That 5x squared over 2 minus x cubed over 3 is the same as 5 over 2 x squared minus 1/3 x cubed from 0 to 6. So all we need to do is to just substitute the lower and the upper bound for x squared and x cubed respectively. So we have 5 over 2 times 6 squared minus 0 squared. We just substitute the bounds for x squared. Minus 1/3, we have 6 cubed minus 0 cubed. Starting with the upper bound minus the lower bound. And that is now equal to 5 over 2 times 36 minus 1/3 times 216. And 5 over 2 times 36 is 90 minus 1/3 of 216 is 72. Getting the difference of 90 and 72, so we have 18. But in the module, the answer of the area is 4.67 square units. Look at the graph on the right. Probably the focus of this solution is the shaded region. And take note that in the module, that shaded region is represented by x. And since the y-axis will be the basis of our computation for the definite integral, so we will be computing for the dy. The integral of x dy from 0 to 6. From the given, the y function is 5x minus x squared. And to get the derivative of y or the dy, the derivative is 5 minus 2x. We will use this dy 5 minus 2x to substitute the dy in our integrand. We have the integral of x times 5 minus 2x dx from 0 to 6. And multiplying x and 5 minus 2x, we have 5x minus 2x squared dx. We will now change the bound since we change from y to x. Take note this coordinate. When y is 0, x is 0. And when y is positive 6, the value of the x coordinate is 2. Therefore, the new lower bound is 0 and the new upper bound is positive 2. And the antiderivative of 5x minus 2x squared is 5x squared over 2 minus 2x cubed over 3. And we will evaluate this using the bounds 0 until 2. We have 5 over 2, 2 squared minus 0 squared, minus 2/3 times 2 cubed minus 0 cubed. So we have 5 over 2 times 4 minus 2 over 3 times 8. Simplifying, 20 over 2 minus 16 over 3. Combining these two fractions, we have 14 over 3. And that is approximately equal to 4.67 square units. In a situation that a problem does not specify anything, take note to follow the assumption of the definite integral. On the right is the graph of y equals x squared minus 3x. And we are going to find the area bounded by the curve from x equals 1 and x equals 2. Because the specified area is below the x-axis, therefore we will be using the theorem that such area is the negative of the integral of our function. The given function is x squared minus 3x, and the antiderivative of this function is x cubed over 3 minus 3x squared over 2. So the area now is the negative of the integral of x squared minus 3x dx from 1 to 2. Applying the anti-differentiation, we have the negative of x cubed over 3 minus 3x squared over 2 from 1 to 2. And that is equal to the negative of 1/3 x cubed minus 3 over 2x squared from 1 to 2. So we will now do the substitution. We have the negative of 1/3 times 2 cubed minus 1 cubed minus 3 over 2 times 2 squared minus 1 squared. We distribute the negative to the binomial, and that becomes negative 7 over 3 plus 9 over 2. Combining these two fractions, we have 13 over 6. Therefore, the area bounded by this curve from x equals 1 and x equals 2 is 13 over 6 square units. We will now proceed to the second lesson in this module. Take note that to solve problems involving areas in the xy plane, remember these three steps. First, we need to sketch the graph. Second, we are going to find the intersection of these graphs. And third, we have to set up the integral. Observe now the first problem. Find the area of the region bounded by the curves y equals x squared and y equals negative x squared plus 3x. Unlike the previous problems, we are only given by one function. In this case, we have two, and we don't have the lower and the upper bound yet. We will now solve these problems following the three steps given a while ago. First, we have to sketch the graphs. This is the graph of the two functions, and the bounded region is the shaded one. For the second step, we are going to find the intersection of the graph. To get the intersection algebraically, we simply just equate y equals y and solve for the value of x. Remember that our first y is equal to x squared and the second y is negative x squared plus 3x. Since y is equal to y, we just substitute those y's. So we have x squared equals negative x squared plus 3x. Combining all the terms on the left, that becomes x squared plus x squared minus 3x equals 0. X squared plus x squared is 2x squared minus 3x equals 0. By factoring, that is now equal to x times 2x minus 3 equals 0. We equate both factors to 0, so our first x is x equals 0, and the second x is equating 2x minus 3 to 0, so that is x equals 3 over 2. Right after that, to get the solution set of this problem, we have to get the value of y using x equals 0 and x equals 3 over 2. For the first value of x, which is 0, to compute for y, I am using the first equation since this is simpler compared to the second. So we have y equals x squared. Substitute x by 0, y equals 0. So the coordinate is 0, 0. And for the second value of x, which is 3 over 2, the same function, y equals x squared, 3 over 2 squared, and that is 9 over 4. So the second coordinate is 3 over 2 and 9 over 4. Therefore, the solution set is the set containing 0, 0, and 3 over 2 and 9 over 4. Take note that on the graph, these 2 points are the intersection of the two graphs. And for the third step, we need to set up the integral. Take note this formula that the function of this kind of problem is the integral of the upper function minus the lower function dx from a to b. And this a to b represent the values of x. In this case, our a is 0 and our b is 3 over 2. Take note on the graph that the upper function is the graph negative x squared plus 3x and the lower function is the graph x squared. By substitution, we have the integral of the upper function negative x squared plus 3x minus the lower function x squared dx from 0 to 3 over 2. Combining the two negative x squared, so we have negative 2x squared plus 3x dx. And the anti-differentiation of this function is negative 2x cubed over 3 plus 3x squared over 2. We evaluate now the integral using the lower and the upper bound. We have negative 2/3 times the upper bound 3 over 2 cubed minus the lower bound 0 cubed plus 3 over 2 times the upper bound 3 over 2 squared minus the lower bound 0 squared. If you simplify that expression, it is equal to 9 over 8 square units. For our second problem, find the area of the region bounded by the curve y squared equals x minus 2 and the line y equals 4 minus x. This is the graph of the two functions and the area of the region bounded is in color blue. Observe that the first function is y squared equals x minus 2 and we can rewrite this in the form y equals the square root of x minus 2 and for the second function is y equals 4 minus x. So we can now equate y equals y. The first y is the square root of x minus 2 and the second y is 4 minus x. To eliminate the square root sign, we will square both sides. So we have x minus 2 equals the square of 4 minus x is 16 minus 8x plus x squared. Combining all the terms, we have x squared minus 8x minus x plus 16 plus 2 equals 0. Combining like terms, x squared minus 9x plus 18 equals 0. By factoring, we have x minus 3 times x minus 6. By equating every factor to 0, the values of x are x equals 3 and x equals 6. To get the value of y, if x equals 3, I am using the second function. Take note, we can use any of those functions, but in my solution, I am using the second one. By using y equals 4 minus x and substituting x by 3, the value of y is 1, so the coordinate is 3, 1. And for x equals 6, the same function, by substituting x by 6, the value of y is negative 2. So the second coordinate is 6, negative 2. Therefore, the solution set here is the set containing the following coordinates 3, 1 and 6, negative 2. Before we can proceed to the third step, let us first observe the difference between the two graphs. On the first graph, if we draw a vertical line on the intersection of their points, the shaded region is in between the two vertical lines. So we just directly solve for the integral of the function. But for the second graph, if we form two vertical lines on the intersection of their points, we can have two areas. The area found on the left of the first vertical line and the second area is in between the two vertical lines. So for this problem, we are going to split the area of these two parts to get the total area. So we will now set up the integral of the first area. Take note on the graph that the first area can be solved by just using the one function, the function of the parabola which is y squared equals x minus 2. By extracting the square root of this function, y is equal to positive negative of the square root of x minus 2. The positive root represents the upper semiparabola, while the negative root stands for the lower semiparabola. Therefore, our a sub 1 is the integral of the square root of x minus 2 minus the negative of the square root of x minus 2 dx, and the lower and the upper bound are 2 and 3 respectively. Look at the graph that the vertex of the parabola is at x equals 2 and the x-coordinate of that point is x equals 3. So we will be using the bounds 2 to 3. The square root of x minus 2 minus the negative square root of x minus 2 is equal to the square root of x minus 2 plus square root of x minus 2. Combining those similar terms, that is now equal to 2 times the square root of x minus 2 dx. Applying the constant theorem of the integral, this expression is equal to 2 times the integral of the square root of x minus 2 dx from 2 to 3. By getting the antiderivative of this function, we have 2 times x minus 2 power 3 over 2 over 3 over 2 from 2 to 3. And getting the reciprocal of the denominator, we have 2 times 2/3 x minus 2 power 3 over 2 from 2 to 3. 2 times 2/3 is 4 over 3. We will now substitute the bounds. 4 over 3, 3 minus 2 power 3 over 2 minus the lower bound 2 minus 2 power 3 over 2. 3 minus 2 power 3 over 2 is 1 power 3 over 2. And the second one, 2 minus 2 power 3 over 2 is equal to 0 power 3 over 2. 1 power 3 over 2 is positive 1. And 1 times 4 over 3 is 4 over 3. For our first region, the area is 4 over 3 square units. For the second region, take note on the graph that we will be using the curve and the line. And also, it is clear that the upper function is y equals 4 minus x, and the lower function is y equals the square root of x minus 2. And for our bounds, since the x-coordinate of the first intersection is 3, and the x-coordinate of the second intersection is 6, so we will be using 3 and 6 as our lower and upper bounds respectively. So for our second area, this is the integral of the upper function 4 minus x minus the lower function square root of x minus 2 dx from 3 to 6. Applying the anti-differentiation rule, we have 4x minus x squared over 2 minus x minus 2 power 3 over 2 over 3 over 2 from 3 to 6. Or simply, this is equal to 4x minus 1 half x squared minus 2/3 times x minus 2 power 3 over 2 from 3 to 6. Let's have now the substitution. So we have this substitution, and the result is negative 37 over 6. Since this is the area of our second region, there is no negative area, so we will just use the positive 37 over 6 as the area of our second region, which will be added to the area of the first region. Therefore, area of the region bounded by the curve y squared equals x minus 2 and the line y equals 4 minus x is the sum of the first and the second area, that is 4 over 3 plus 37 over 6, and that is equal to 15 over 2 square units. For some additional examples, let us consider the two problems in lesson 3. Find the area bounded by the curves y squared equals x and y equals x cubed. Solve the system, then find the solution set. First, let us sketch the graph. This is the graph of the two functions simultaneously, and we can see that this graph is located in quadrant 1. Do not mind anymore the other variables found in this graph. Next, we are going to find the intersection. The first function is y squared equals x, and this is equal to y equals square root of x. And the second function is y equals x cubed. By equating y, we have square root of x equals x cubed. We square both sides to eliminate the square root sign. So we have x equals x power 6. Combining all x variables on the left, we have x power 6 minus x equals 0. And by factoring, we have x times x power 5 minus 1 equals 0. We equate the two factors to 0. So the first value of x is 0, and the second value of x is positive 1. When x equals 0, by using the second function, y is also 0. So the first coordinate is 0, 0. And if x is equal to 1, by using the second function as well, y is equal to 1. So the second coordinate is 1, 1. Therefore, the solution set is a set containing 0, 0, and 1, 1. We are now on the third step to set up the integral. Go back again your attention to the graph. If we will form vertical lines in the intersection of their points, the region bounded by the two graphs is not divided. So we can directly set up the integral by using the upper function y squared equals x minus the lower function y equals x cubed. To compute for the area bounded by the two curves is to get the integral of square root of x minus x cubed dx from 0 to 1. And our answer is 5 over 12 square units. And for the last problem, find the area bounded by the curves y equals x cubed minus 4x and y equals x squared minus 4. Here is the graph of the two functions. And if you will observe, it's quite complicated because we have two regions as the intersection of their graphs. Aside from that, if you will observe, there are three intersections of their graphs. So later, we must have three coordinates for the solution set. To get the solution set, we will equate y equals y. The first y is x cubed minus 4x equals the second y is x squared minus 4. Combining all the terms on the left, so we have x cubed minus x squared minus 4x plus 4 equals 0. By regrouping, the first group is x cubed minus x squared, and the second group is negative 4x plus 4. Factoring the common for the first group, the common is x squared. X cubed divided by x squared, so we have x, and negative x squared divided by x squared is negative 1. So we have that x squared times x minus 1. And for the second group, the factor is negative 4. Negative 4x divided by negative 4 is x, and positive 4 divided by negative 4 is negative 1. So the second factor is negative 4 and x minus 1. So we get the outer factor which is x squared and negative 4. So we have x squared minus 4. And the common factor x minus 1. So the simplified factors of this equation is x squared minus 4 times x minus 1 equals 0. We equate the first factor to 0. So x squared minus 4 equals 0. X squared equals 4. And by extracting the square root, we have x equals positive negative 2. And for the second factor, x minus 1 equals 0. So our x is positive 1. So we have three values of x, negative 2, positive 1, and positive 2. If x is negative 2, using the second function, y is 0. If x is positive 1, y is negative 3. And if x is positive 2, y is 0. So the solution set is the set containing negative 2, 0, 1, negative 3, and 2, 0. For our third step, take note of this graph. The graph is divided into two regions using the three vertical lines. Therefore, to get the area bounded of these two curves, we need to add the area of these two regions. The first region is from negative 2 to positive 1, and the second region is from positive 1 to positive 2. Here is the formula of the area of the first region. The integral of x cubed minus 4x as the upper bound minus x squared minus 4, the lower bound, dx from negative 2 to positive 1. This is equal to x cubed minus x squared minus 4x plus 4 dx from negative 2 to positive 1. The antiderivative of this function is 1/4 x power 4 minus 1/3 x cubed minus 2x squared plus 4x from negative 2 to positive 1. Let us now proceed to the substitution. Just go on the process of substitution. Negative 2 as the lower bound and positive 1 as the upper bound. The area of the first region is 45 over 4 square units. We will now proceed to the area from x equals 1 to x equals 2. Take note that on that portion, the upper function is y equals x squared minus 4, and the lower function is y equals x cubed minus 4x. Therefore, the formula of the second area is the integral of x squared minus 4 minus x cubed minus 4x dx from 1 to 2. And the antiderivative of this function is negative 1/4 x power 4 plus 1/3 x cubed plus 2x squared minus 4x from 1 to 2. After that, we substitute the upper and the lower bounds. We have the area of 7 over 12 square units. To get the total area bounded by the two curves, we need to add the first area and the second area. The total area equals the area of the first region plus the area of the second region. The area of the first region is 45 over 4, and the area of the second region is 7 over 12. And the sum of this fraction is 71 over 6 square units. If you will try to convert this into decimal, this is approximately equal to 11.83 square units.